there is no point in further introducing myself. But anyway, I have a small slide on that. I will just highlight some portion of it only. No. Wait, madam. I'll tell you when to go to the.
Okay, sir. Okay, sir.
Yeah. Okay, so today's discussion is broadly on introduction to autonomous systems, and I think you have sequences of discussions or lectures on these different aspects of autonomous systems. This specific talk is mainly on the some broad generic discussion on the autonomous systems, and at the end, if time permits, we will have some more specified discussion on some aspect of autonomous systems. Yeah, madam, please next slide. Okay, so this is kind of my career affiliation details. I would just point out that at the present, I am, as mentioned already, I am a faculty at the Aerospace Engineering Department of IIT Madras. And presently, 8 research students are working with me, and 5 MTech students, MTech course students, and 4 BTech course students. They are working with me for their projects. And in the past also, like several project students have already passed from me, and all of them have gone out with very nice publications, very nice works in the area of motion planning, guidance, and path planning. And one of the important aspects of autonomous systems
Sir. Sir.
Radhika, is the screen seen?
Screen is seen, ma'am. I couldn't hear, sir. Are you able to
Yes,
hear?
even I couldn't hear. Sir, you are not audible.
Yeah, there are some. It looks like quite unstable today. The link is. Uh, can you please? Am I audible?
Yes, sir. Yes, sir. Now you are
Yeah.
audible, sir.
Yeah. Okay. So, okay. So we'll not waste time on this slide. So anyway, I was just trying to point out that we have an active research group with numerous students in our group, and they are really producing some high quality of research in the area of motion planning, path planning, and guidance. Yeah. Please next slide. Okay, so broadly, I will first introduce what we mean about autonomous systems, and then we'll talk about what are the different potentials. Like, of course, it has a huge potential. That's why it's a buzzword now, autonomous systems. But again, with all these buzzword things, it always associates with some challenges. So we'll talk about those challenges in brief. And then what are the possible visions in terms of, we'll be mainly giving a vision from the US Department of Defense, US DoD document. Then we'll give one example where we'll try to give you further motivation of such autonomous systems where you see the different kinds of asymmetric agents are working how to achieve something finally and in an autonomous way. We'll talk about potential applications and why I am calling it as potential, because some of the applications in industry they have started working on, but again, like we are far away from autonomy in a broader
Sir,
sense. We have achieved autonomy, of course, in to some extent in several applications, but most of them are still potential applications only.
స్ఫూర్తి వాళ్ళు
So we'll also talk about when we
అడ్మిషన్లు
say
తక్కువ
potential
ఉన్నాయని నిన్న
application,
పిలిచి
also
ఒక
like
10 మంది నాన్
as I'm
టీచింగ్ని
giving this
జంప్
justification why
చేయాలని.
I'm using the word potential, also we need to understand that what are the different autonomy levels? What do we mean by when we talk about autonomy levels? Right? What are the different autonomy levels we'll talk about? And how people look at it, like globally, many different
ఇక్కడ
people look at it differently. So we'll look
అదే
at it
అనేది
that way.
చెప్తున్నా, జస్ట్ చెప్తున్నా ఇన్ఫర్మేషన్ అంతే.
Then we'll touch in brief the different components of an autonomous system and what are the broad characteristics of them. But in more detail of each of them, you will be, I hope that you will be also learning in I mean, in due time in the course, because we will be having more dedicated lectures on that, I hope. A schematic I'll be presenting then that how the workflow goes on in an autonomous system that we can visualize. Different research directions, of course, is a subset of altogether research directions, but we'll talk about some of them. And to the end, I will talk about motion planning and some basics of it and classification. Madam, next slide, please. Okay, so to introduce autonomous systems, first let's define what is an autonomous system. It's nothing but an engineering system. So mostly we talk about man-made engineering systems. So how is it different from any other man-made engineering system? It is different in the way that we expect it to learn from the environment, right? It is normally any system, it works in an environment. Now environment means it may be like, to give an example, right? For example, suppose you have an unmanned vehicle and you want it to go from point A to point B, right? Now that point A to point B, how to go it has its onboard sensing limitation, of course. It may have, of course, GPS feedback. So from that, it may be knowing that, okay, this direction, this road and that road we should be taking. Also, it would be knowing that, okay, there are this grounds and all that may be obstructing the path for today. Okay, so there are many such things. So essentially, what I'm trying to say is that GPS may give you an overall feedback, but locally you have to understand what is there exactly, right? You cannot, if the traffic signal is saying that not to go, you cannot go just like that. So it should be learning from that signal as well. You should be learning from the directions, whichever is shown on the road. You should be learning from that, and accordingly it should adapt with the thing. So and when it adopts its behavior with this, so of course it can modulate its decisions and then act accordingly. So that's why, like, we can, in one sentence, if we have to say, we can say it as an engineering systems that can learn, adapt, make decisions, and act. Now, when we say autonomy, what do we mean by autonomy in what? As I gave you just one example, in that you hopefully you have already understood that first the vehicle had to understand, right, where it is, right, and then analyze that okay, these are the situations. So first you have to have that recognition that what are the situations there, and then from there the analysis will come that what to do. And this why to do part would be very much associated with this recognition part, that where you are actually, how you are behaving. Okay. Now, once you are pretty much clear, once your system is pretty much clear about what to do and why to do, then of course you need a decision on when to do and how to do. So in this example, when to do means like when the traffic signal will go green, then you should start moving, right? You should not stay just idle there. So deciding on when to do, and of course you have to know how to do. You may want to change a lane sometimes. You may want to go to another different road, so you have to make a turn, or you want to go straight, whatever it is. So you need to decide how to do, right? And also, like, when you are doing when we are saying that how to do this, decision is an outer loop thing. I'm still not talking about the low level part of the system. Then of course, like, low level part, no, madam. I will tell you, madam. Low level part will come just after that, when we say that implementing the form decision, right? There, this low level control is very much important, because then you are really talking about the dynamics of the vehicle, and like whatever are its limitation because of its dynamics and the kinematic behavior. So based on that, you have to know that how to implement that form decision. So the low level control will be doing this job. Yeah, madam, next slide. Okay, so when these decisions will be left to the systems, so we can say, okay, of course you can put it in many different ways. One way to put it as, like, when you feel that, okay, human control may become too expensive in some cases. So there you may feel that, okay, use of autonomous systems may be very helpful because it may save you lots of money. That's the number one. Number two is that when you may feel that okay, human involvement may be quite infeasible. Now, infeasible, how, when it can be infeasible? It can be infeasible in the ways like, okay, so suppose if at the some forest fire monitoring, if you want to do, right? Forest fire monitoring, if you want to do, it's always an easier job to deploy an autonomous unmanned systems. They can go and they can just try to locate the exact periphery of the forest fire, and then they can also relay the information to the control station that okay, this is the mapped boundary of the forest fire till date. So you can send immediately some task force and all that, which can help in this. So this kind of situation, like okay, here it may be directly infeasible by human, or like it may be infeasible means it may take lots of time or it may take lots of effort for human to do. While an autonomous system can be deployed quite beneficial. Then the next thing is that when the human effort is really impossible, like human, of course, like they work quite quickly. There is no doubt about it. But again, like you know that when you have multiple of the tasks and all that, everything has to be done quickly. Then it's not that always human can take the decision so quickly. In several cases, like an autonomous system can be of help, can be of much help. And it's an estimate, of course, that Persia, but there's this annual worldwide economic impact of this autonomous systems by 2025. So they they are estimating it to such a big value, $1.7 trillion to $4.5 trillion. Yeah. Okay, this next slide. Okay, now what are the different potential? What is the potential? Then what are the challenges? And then what's the vision? Okay, of course we can understand that why all on a sudden all these things, autonomous systems, autonomous vehicles, everything we are talking about, because and earlier we are not talking about. If you look at the history, right? Of course there were this kind of notions pretty long time back as well, but that time the this communication was not that much developed, or the computational facilities were not that much developed. Also, your like actuation, if it is completely mechanical, it is not always that efficient in terms of the energy efficiency and all that. So with all this, like with, if you notice that last 2 to 3 decades, the rapid advancement has happened in each of these aspects, right? And of course, like with rapid advancement of in each of these aspects, which are very much related to the technology related to this unmanned vehicles or autonomous vehicles or robots, naturally there have been a significant improvement in related technology as well. So as we have already discussed that it, of course, it involves like cost effectiveness. This is one key thing. Then it involves less human risk in operation, right? And there are like, if you are talking about smaller systems, smaller vehicles, or like swarm of smaller vehicles or smaller autonomous agents, then you have convenience of portability as well. I'm not talking about bigger, very big UAVs in this particular point, but you have multiple of them in smaller scale, then you, of course you have convenience of portability as well. And as a result, like you know that once you have autonomous vehicles coming up, the technology of autonomous vehicles getting improved very rapidly, could be seeing like the autonomous systems. Now, what is an autonomous system? Here is a collection of autonomous vehicles, autonomous robots or autonomous agents, right? Why I'm saying all these things, because some of you may be familiar with that. Okay, this robot may be an autonomous system, completely autonomous system to you, then the different parts of the robots will help to build up the autonomy of the system, right? Now, to somebody else, it may be that that a collection of autonomous vehicles, or just itself one autonomous vehicle is an autonomous system, right? Because again, like different components of it will build up the autonomy of the vehicle. To some people, it may be like okay, a collection of such autonomous vehicles or robots that may form the autonomous systems, because I mean, what are your subsystems? What are your components of the system? That completely depends on the application, whatever you are working on. So with the improvement of this technology of autonomous vehicles, of course, the autonomous systems in general, I can say, it has also seen a steady increase in applications. Next slide, please. Okay, so now as a collective system, any auto, yeah, anybody is asking anything? Okay. Okay, as a collective way, an autonomous system, of course, will be having several advantages. What kind of advantages we can conceptualize? We can think about the improved perception and sensing. Of course, like if you have one agent in a system. Okay, so the way I have put in the slides, essentially, I consider it more from a bigger system perspective, where you really have multiple autonomous agents and all that, and that would, of course, no, but even like if you consider in a smaller in a robotic system, just single agent system, also then also you know that multi-sensor data fusion, this kind of concepts are very much there. So essentially, it improves your perception of sensing in whatever way it is possible. It tries to do that. It improves your reaction time, so you can actually react in a smaller amount of time, so it may have that advantage as well. And naturally, if you can have both of these, then you know that overall performance of the system can be further improved than just a manned system. Okay. Safety and reliability, right? Reliability is kind of again, like I'm not really talking about in terms of the pure reliability in terms of the statistics of it, but what we mean is that you can have for a dedicated application, you can develop a reliable system, which may have some sort of redundancy in the system, and then you know that okay, this will perform reliably. Because like you know, if you know that okay, one of the motors may be failing, but the other one will be taking off from there. So that kind of logical flow, if it is there already inbuilt in the system, then you know that you can also achieve reliability in that sense. And naturally, you can also enhance the safety of the system. It can become more fault tolerant. So there is a possibility like you can do how you can do. Okay, then of course, like human burden, like human personal burden, it involves reduced human personal burden, uh, which may lead to different operational advantages and also like cost saving as well. Okay, then another important thing is that there may be several situations. So as I told that you may have a GPS feedback in the given example of the autonomous car which is going on a road. So, but again, consider a situation where it is a GPS denied environment, right? Or which where it is a kind of you have some signal, but it's so poor that you cannot use it reliably. So then, this kind of autonomous system, if you have really embedded autonomy into a system, then it will help you to even perform in those kind of environments also quite efficient. So that is also very added advantage of having a system really autonomous in that way. Now, what are the challenges associated with deployment of such autonomous systems? One thing is that it has a reduced flexibility in intelligence. Now, what do we mean by reduced flexibility in intelligence is that the most problem is that if you talk about absolute autonomy, there is nothing called absolute autonomy. So you cannot achieve an absolute autonomy in any possible way, because I mean we can of course dream of it, but whatever you can dream, you will see that whatever system you are thinking about an autonomy on, or whatever set of problem you are thinking as an autonomy on for a system, that set of problem is of course a subset of a bigger problem, right? So for example, in this case, like when we are talking about that point A to point B, an autonomous vehicle is going, right? Now you are giving the start point and the end point, and then it is going in autonomously, that's fine. So it may have the autonomy over the operations of driving through the portions right? Driving through the portions, following the rules, following whatever logics are there, right? But again, like somebody is giving it the input of the destination point. So this point B is like, who is now fixing? There is, okay, now you can say that, okay, I will have another loop of outer loop of planner which will set my point B. Yes. Okay, now then the next question will come, that how that outer loop of planner will set that point B. Again, there must be some criteria. Now, who is fixing that criteria? Which system or which subsystem is fixing that criteria? So again, you will see that in this layered way, you will keep on seeing that that if you think about a full autonomy in the system, it is almost uh, not possible, or also it is meaningless to ask even. So what it makes sense is that if you ask that, okay, over this set of functions, whether we have achieved autonomy. Now, as you can understand that by now, that okay, now uh, I have an autonomy, level of autonomy, and over some functions of that is to be performed by the system, right? Now, suppose there is some other kind of task has come, right? It's not that the environment has changed, everything has remained fixed, but all on a sudden, if you have to divert to some other kind of task, which the system was not prepared for before deployment. This kind of flexibility you cannot have. While, like, of course, you know that as a human, you once you are in some work, then all on a sudden something else comes, then you change your priorities and all that, right? So you have as a human, we have our knowledge of our overall world, right? But to put a knowledge of the overall world to an autonomous system is still a distant future thing. So that's why that it has its reduced flexibility in intelligence, and also it is in terms of the robustness in performance. So far till date, we are far away from achieving autonomy. There are lots of theory, there are lots of like theoretical results which show that yes, we can do many this and that things. But when it comes to practice, in many of the most of the cases, we are far away from the robustness. It is more specific when your environment is very much more complicated, much more complex. When your environment is a bit simpler, when you can have lots of calculations a priori, when you can have all lots of logics embedded a priori, then many things are quite easy to achieve. But again, when things are not really like that, then this robustness problem comes, and it also comes at the cost of like so it also comes like when in other forms as well, that you may require, as I told in the earlier point, that it may achieve reaction time faster reaction time, but again, like you know that when you have very complicated algorithm involved in it, which will be having like a huge computational burden, it will be automatically leading to a higher time requirement, right? So in many other ways, actually it poses severe challenges. No, madam, please, in the earlier stage. Yeah. So, so this is the first point, and then difficulty in decision making about which tasks to allocate to such systems. So, when you are talking about again an autonomous system, so again and again I'm saying that you have to define the set of tasks on which you are expecting the system to perform autonomously. There is another set of problems, right, or super problems or sub problems, for which you are not actually taking the help of that system. Now, how to make this decision that which part will be allocated to that autonomous system and which part would be manual done and all this thing. So all these challenges come up when you are going to deploy an autonomous system that rests. Yeah, madam, next slide. Okay, so as a result, of course, like this, there is some vision that all these policymakers and defense groups and all that they come up with. So there has been like a vision of this U.S. Department of Defense that is mainly for different kind of unmanned vehicles. What they are trying to say is that they want to achieve in like in some another decade or so, they want to achieve a level where they can talk about a very seamless integration in this overall decision making process, right? Different and also like decision making process and then actuation process and everything, right? Whatever you can associate with an autonomous system, right? All these diverse unmanned capabilities, right? So with all these things, you also want to see that, okay, now you are also having an operator. If you want to have an operator also parallelly, the system may be working autonomously, but there should be a seamless integration of this manned and unmanned things, right? So there should be a quite good merger of manned capabilities and unmanned capabilities. So that's what they are now thinking about. And of course, like as a result, they are talking about UX teaming up with this manned systems. So this MUM, that's what they call it. So all these things, like essentially, again to stress the point that uh, there is nothing called absolute autonomy. So we have to agree that, okay, whatever we try to do, there has to be some human somewhere, right? It may not be in the system, but somewhere. But again, when we have that, there should be a seamless integration in the overall process of their different capabilities, right? So okay, with this we will go to the next idea. Okay, so this is an example just to give you a motivation that what we are, what we mean when we are talking about an autonomous system. So this is a practical example from one of the oil infrastructure on the kind of on the seashore. That is a lateral oil infrastructure monitoring system, and this is also taken from the DoD document. So here you have a lateral combat ship LCS that is just used there for like having a surveillance over the seashore, and there is a oil pipeline and like massive oil project is there. So essentially they have to secure that place, and there are like they call it some enemy agents. Can do some damage, or like, I mean, damage means they can use it in a different way. So what they are trying to do is that they are deploying this lateral combat ship. So it's a part of this entire autonomous system very much. And then you have one center, that is Joint Maritime Operations Center, JMOC. So this LCS is having a link with the JMOC, but again at the same time, uh, all on a sudden, just to have some more feedback about the system, so it is also deploying some small tactical unmanned aircraft systems. So that is STUS, and is also deploying another unmanned underwater system. Okay. So with the help of these two, then it is trying to understand what is exactly happening to this oil pipe or oil infrastructure. Then once it senses something wrong, it immediately, the US immediately sends a signal to the stewards, right? And once the stewards gets the signal, so it also relays it to the LCS, and LCS in response, they to facilitate the detection of the anomaly, whatever is happening there, is also engaging one communication buoy there, and that the communication buoy helps in further enhancing the communication. So because you know that when you are communicating from farther away, so there would be some latency and all that. So the communication buoy is trying to help in this aspect. And then it's also the US and the stewards also helps to connect to the JMOC more efficiently. And as soon as the JMOC gets the confirmation that yes, really there is some encroach from some enemy agents, so of course, like they would be sending the force immediately to neutralize the agents. So this is the overall system how and all these things are being done autonomously. Now again, this is an operation that is being done autonomously. Now if you say that okay, how it was decided that LCS will be going there, or how the motion of the LCS will be controlled. So how it was decided the LCS will be stationed there, it's a part of human decision, right? It's not a part of an autonomous decision. It's a part of human decision. Then how it will move is a kind of combination of manned decision and an autonomous decision. Of course, locally it has to have more kind of autonomous facilities, because from remote you cannot control everything. And then of course, like how the JMOC is working there. The JMOC is working there. There also like the man intervention is very much there. So as you can understand that in the system, of course, like to some extent they have an autonomy in detecting the anomaly in the oil infrastructure and relaying the information to the demo. So this part is done in a quite autonomous way. So that's how this is a very good example of such autonomous system. So next slide, please. Yeah, next slide, please. Okay, so with all this, like now we are in a position to appreciate that what are the different potential applications of autonomous systems. Of course, like we can think about like different military operations and different civilian operations. Right? So in the military operations, wide range of military operations, like you know that okay, in the battle space, like you need more and more awareness, right, locally, and also like in an enhanced or like in an expanded over an expanded region, and of course you need to have a proper environmental sensing. So you need to have a proper weapon detection mechanism, and then counter weapon capabilities as well. As I gave you one example, that oil infrastructure monitoring. So you need to have like this kind of port of or station security, then precision targeting, precision strike, then you need to have like surveillance, those ICR kind of applications, ICR and C2 kind of applications, right? And then you see that okay, there are other applications like you have exploration, right? Space exploration. Then or you want to have more ocean exploration for different mines or oil field and whatever. Then also you may have like the different forest explorations and mine explorations as well. There are different applications also in the sense of intervention and rescue, right? So you may have heard the term like search and rescue, right? Essentially, what we talk about is that there are several people who have been maybe stuck somehow, or like even animals also, they may have got stuck in some position because of some calamity and all that. It may be fire, earthquake, flood, disaster, whatever. So you can deploy an autonomous system which will be immediately giving you the feedback that okay, there are this many people it can locate, that okay, they have to be kind of rescued from those places, and then so it can help the work of the dedicated manned force for that. Okay, then in agriculture, like particularly it's called precision agriculture. So what does it mean? It means that like in starting from the very first part of the farming, like you prepare the land. So how to monitor whether the land is prepared, how to put the seeds and all that. So when you are putting the seeds, whether it has been sprayed over uniformly and all that. So to look into all these aspects, then again at the end harvesting and all that. So in all these applications, you have the autonomous systems can be deployed quite quite meaningfully. Next slide, please. Okay, in industry, like you know that okay, different kind of manufacturing industry, all like the real estate, buildings and automobile industry and all that. Everywhere, like whatever, wherever you want to achieve some functions, right? Some functions maybe you want to kind of make some part of it of the production process completely autonomous, right? So before that part, it may have manned part. After that part, also it may have a manned intervention. But that part you are keeping it autonomous. Of course, it may be with some human supervision, but more or less it's autonomous. Also, you may need a kind of monitoring of the job flow in the shop floor there. So for all these things, you may effectively deploy autonomous systems. And you already know that in logistics and all that, so already you have seen the like the videos of Amazon and all that. So they are just trying to explore different possibilities of like delivering something with unmanned aerial vehicle, something like that. Of course, in warehouse operations, like you may have mobile robots, like ground mobile robots, which may be very much effective, like in picking up the items and putting it in proper place, or monitoring whether what is the stock level and all that. So for all these different kinds of applications, this autonomous systems are again meaningful. Inspection, yeah, inspection means like you may have stricter regime of inspection in construction site or like power transmission and distribution line. You may need to understand that where is the fault or whether at all some fault is there in some segment. Even there are like different parking lots, right? In parking lots, you know that uh, okay, of course, like in India, it's not really that common, but again, like if you see in other, I mean, this we have parking lots, but again, like monitoring a parking lot is not that common by autonomous system. But again, in several countries, they deploy like UAVs and all that to kind of have a continuous watch on the parking lots, so that no mishap happens there. And if mishap happens, then help the police, okay, how it happened and all that. So they have this. Okay, so then of course in medical applications you need like for telesurgery, right? You may have a autonomous robot system which will be helping in the telesurgery. Then in ward monitoring in hospitals and health centers. For example, this is more specific now in the context of COVID now. You may be seeing that, okay, like there are situations where like it's not always possible with just normal dress to go to several wards, right? So you can say send the set of like autonomous vehicles somehow to monitor the things, monitor the different wards. So in this way, like different applications are there for this autonomous systems. Next slide. Okay, so overall, like, okay, you can say that, okay, if you have another this constraint teleoperation kind of things, right? Where you are sitting somewhere, but all the functions are happening in some other place. So those operations, so to have this kind of constraint teleoperations, uh, then like when it goes beyond our sensing and control capabilities, like human sensing and control capabilities, so you can uh, think about autonomous systems. Of course, like multi-agent systems form a big part of this autonomous system discussion. We can work quite cooperatively different tasks, right? And when you can do it in a cooperative way, you can talk about several consensus kind of problems. You can talk about also in a cooperative way, you can also target, you can go for some interdiction mission if you consider a threat to your autonomous system or over to your overall system. So with the multi systems, multi-agent systems, you can actually help it to you can help the overall system to enhance the overall collective capability further. Okay. Now complexity of platform and tasks overload our cognitive capabilities. So again, like it is also pretty much related on with the sensing and control capabilities. So in between sensing and control, you need to have this cognitions, right? So cognition means suppose you are walking on a road, you should be understanding where you were standing at some point of time, maybe. You should be understanding that okay, whoever else is there in your periphery. You should be also understanding where you are heading. You should be also understanding whosoever is in your periphery, where they are heading. So all these things you need to understand, right? So so our brain really does a complicated task already. But again, like there may be some limitations in several cases where we fail, our cognitive capabilities fail. There probably autonomous systems can have more applications. Yeah. Next slide, please. Okay, now let's talk about we have been so far talking about many times autonomous systems, autonomous systems. Now, what are the different autonomy levels? What do we mean by autonomy levels, right? As we have discussed, what we mean about autonomy, we mean autonomy about that like it's the capability of analyzing what to do and why to do, right? And then you decide that okay, when to do and how to do, right? And then you just go on implementing that part, right? So this is again you can understand that this what to do is very important. We started with what to do, right? Now this what to do is why it is very important. We are specifying that you are talking about some specific set of tasks. Only that you are talking about the autonomy, right? So we will come to the end of this autonomy levels portion to that part again. Now, when people talk about autonomous systems, different people say it in different ways. Like even human machine command and control kind of situations are also talked about. I mean, several regimes you will say that they will say call it as an autonomous or automated system. But actually, you can consider them in a two different classes. Like one is semi-autonomous, which is a kind of human in the loop, Now, in which like the system basically requires the regular human inputs and intervention for successful working. And there's the other set of this kind of application where you have a human supervised, autonomous, or human on the loop, not in the loop, right? Now, in human on the loop situations, essentially the system can work on its own, right? At least the specified job it can work on its own, but it does it with the human monitoring. So the human is very much there for the supervision purpose. So it does it with human monitoring. Then the next thing is coming as the sophistication of machines decision making. So there are people, then they will say, no, 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 this is not anyway autonomous, right? It's just a kind of, you can say it as a semi-autonomous thing. So then people say that, okay, why not we talk about some, embed some decision making thing into the machine, right? Why not make the machine more intelligent? Again, in this, like, people call it autonomous, but they actually talk about three different aspects. The first one is some automatic thing, right? In automatic thing, you have some simple rules which are embedded into your system. Now, if those rules are satisfied, then something will happen. Then the system will behave in some way, right? So simple rule-based system, like if you have the relays, so you must have seen that in case of fault, the relay has tripped off, right? So there is a rule that has been set somehow, like it's a mechanically or electrically or whatever, you are setting some rule, right? That rule in particular in this example is of course an electrical example. Now there are of course several mechanical examples as well. So where you can set some simple rule, and based on the physical properties of the system will be working on to respond that whatever input is coming based on that, right? Then the next thing is that automated system, right? So if you see the earlier days relays, then you have seen that, okay, automatic relays, they really talk about it in a great way, right? Because it really relieves people from lots of human efforts. Otherwise, your all appliances, electrical appliances, will burn off. Like if it is not tripped in proper time. Okay, now automated means what? The difference is that here you are embedding more and more complex rules. So it has a complex rule-based response to different environmental inputs. One ideal example is a self-driven car. So there have been given all the rules to drive safely on a road, and how to navigate through different portions from like one road to another road, or changing the lanes, or seeing the traffic signals and following it. So all these things are given, embedded in it. All these rules are embedded in it. It just executes that. It just senses, cognizes that what is happening around it, and then accordingly work on it, right? So it is of course much more complex rule, but it's still it's not autonomous in that. Now, what is an autonomous system? An autonomous system, you will say, I mean, if you are to really again think about in a set of problems, an autonomous system, you mean that, okay, then it has to be kind of self-direction in and self-learning about an environment, right? It has to self-direct itself in an environment while self-learning about the environment. And in the process, there will be several emergent behaviors that would be coming, right, which you didn't embed it at the beginning, right? It will learn from the system, and it will also undergo some behavioral evolution in due process. So, I mean, one example, like, of course, like there are some examples where they show that, okay, a robot it was not able to walk at the beginning, but then it has learned from the different aspects of the environment, and then it has started working also. So this is called something like emergent behavior. So it involves its own behavior. Now, the point is that all these things, like I have tried to show here 5 different scenarios. All these things, many people in different contexts, they refer to them as autonomous systems. Okay, next slide, please. Okay, now, like as I was telling that, I will just give you a little bit more about this, that what is the difference between this autonomous versus automated, right? So I have already told you, it of course depends on the degree of human intervention. Now, as an example, like if you have this driverless car, and if you consider an autonomous car, you can think about them quite synonymous, right? Because a driverless car, truly a driverless car, should have the capability to kind of learn from this environment and then also work on. So it may be like it should not be. Suppose there is all on a sudden a tree has fallen on the road because of some storm. Now, a self-driving car, right? A self-driving car may have that capability if it is embedded from the beginning that, okay, if you see this, you read this as a fallen tree and then work accordingly. But if it is not already embedded, it will not be doing. But a driverless car, because it knows that, okay, a human is there. If needed, a human can immediately step in and then take action, right? But a driverless car must have this capability to recognize that, okay, this is an obstacle. I should not go and hit, right? So this is how kind of full autonomy and partial autonomy or automated parts, these are different. Okay, next slide, please. Next slide, please. Yeah. I am giving this different autonomy levels from document from Singapore Defense, and where they have tried to kind of come up with different levels of autonomy. So at the beginning, of course, you have everything manual, so nothing like autonomous functions. So human controls all actions. Then you have the next level where you have onboard decision support, where all the actions are taken by the human operator, but the autonomous, there is some system which is helping it to take those decisions to put these actions into place, right? For example, like one easy example to visualize is that now suppose in your system, in your laptop, computer, desktop, mobile, whatever, when you try to do some online shopping, right? Then the online, like when you are just trying to put some online order and all that, then you will be seeing that, okay, it is suggesting you something based on your earlier purchases, right? So there is a decision support system. So I mean, it may be annoying at times. I know, I understand, but again, like to many people, many times it helps actually. Oh, okay, yeah, I needed that time. This time also, I actually needed, but I forgot. So it may be helpful, right? Then the next thing is that on and offboard decision support, right? The earlier one, of course, like the example I gave, it is a kind of internet-based example. But again, the similar example you can also think about in just when you are on the same vehicle and then there is a support system there, onboard support system. Similarly, of course, like you have a tele-operated decision support system, so that is an offboard support system. And then you have the next level that I told a couple of slides back, this active human in the loop, right? So the decisions and actions are performed by the system, of course, with regular human intervention and inputs, right? Now, of course, the data support system can come on and on or off board. That's okay. But again, the next level comes as the human on the loop, right? Which is in which human behaves as a supervisory agent, right? So everything is like whatever set of tasks is allocated to the system, it is done by the system autonomously, but with some human supervision, so that like if something goes wrong, even in a slightest possible way, the human can intervene and then reset the system or correct the system accordingly. Right? Essentially, what we mean by intercept and override. Then, of course, you have one level of fully autonomous. Again, in fully autonomous, they have characterized it in two classes. First one is that it is everything is done in that set of problems. Everything is done by the system autonomously only, but it's still like very rarely supervised. Like it is, so it's not like a continuous supervision of human is there. It's like, okay, sometimes maybe a sampled supervision is there. It's a very rare sampled supervision. And of course, the top level is that all the set of tasks it is doing completely unsupervised. So that can be considered as a maximum level of autonomy, in at least in a set of allocated jobs. Yeah. Next slide, please, madam. Okay, now, so this is like, as I was telling that by now, hopefully you have understand, because again and again I have talked about that, okay, at least in the set of given tasks allocated to the system, right? I'm not talking about just an autonomous system as a single place. I'm always trying to attach this. So it's actually meaningless to call a system like this kind of autonomous or semi-autonomous. If you don't specify that, okay, you have an overall set of tasks and which part of it is automated or made autonomous by the system, or allocated to that system. So we should always, like, the autonomy rather could be characterized with tasks or functions profiles, right, to perform by that particular system, instead of just characterizing the entire system as an autonomous system. So this is from a document of NATO, which they are giving from they are giving different perspective of autonomous systems, and they are specifically highlighting the different kinds of I think in some earlier slides also I cited some of the things from their report, where they're just trying to show that, okay, of course it has its potential, but it is coming with its challenges as well, and what are the different challenges, and also what really should be made by autonomy levels, what should we mean by autonomy. Yeah. Okay, next slide. Okay, now so was there any other slide we missed? I just so what is slide 16? Can you please go back? Slide 16. Oh, okay, fine. Yeah, please, next slide, please. Okay. Okay, so once we are done with our understanding with autonomy, different autonomy levels, let's go to the discussion of different components. Again, like, it is a kind of very overview of the things. So the details of it, I hope that in other lectures you will be going through. Okay, so we can broadly classify different components as domain-specific aspects and domain-independent aspects. Now, domain-specific, or some of them call it as a platform-specific, some of them call it as problem-specific, whatever. Domain-specific aspects are mainly coming from the different mechanical aspects of it. So you have some agents that are working in the system, right? Or like some bodies or some manipulators which are working in the system, right? And when they are working, they have their mechanical behaviors, right? So it can be related with the kinematics and their dynamics and all that, right? So all these things are to be considered, right, encapsulated in there. Either they are used for manipulation, in case of manipulation, in case of agents it may be just a motion. So it affects the manipulation or the motion or the mobility, right? Also, you have the power requirements, right? It's coming from the one part of it is coming from the electrical aspect, and the other part is going for the different electromechanical aspects, I would say. Okay, now the next thing that is coming as like sensing and communication mechanisms. Based on your environment, based on your problem setup, you actually have a limitation of your sensing and limitation of your communication. You may be in a GPS denied environment, or you may be in an environment where GPS cannot be relied because the data is not coming properly. For example, if you are going to a city, right, if you are going to a city where too many high rises are there, like high rises means like all together you'll see like too many uh, 10 floors, 15 floors, 20 floors, 25 floors, like this kind of buildings are there, too many of them throughout the whole city. Or maybe you are you are in a place where it is too much cloudy, right? You will see that the GPS does not work well quite naturally, right? Because if you are aware of how GPS works, how you receive the GPS signals, you've been knowing that, okay, it is not bound to work well in those kind of environments. Now, I personally have faced, like, if you I mean, if you ask for Uber to come in those kind of environments, Uber will come somewhere else, and it has happened repeatedly. So in some of the cities in the US when I was there, so like it used to happen quite regularly. So it used to be a problem. So there people, that's why they prefer, instead of Uber, in particularly those cities in those portions, they prefer, rather if they have to go by a cab, they go by a regular cab than by a Uber. Although Uber, it would be cheaper than a regular cab. Yeah, so these are the, so I just gave you one example because there is a limitation of this communication that may come. Also, there is a limitation of sensing in the way that if you don't have the GPS feedback, you will not be having the feedback of all agents in this. Is there any question from anybody? Somebody has unmuted. If there is any question. Okay. So, okay, so with this, like you have this sensing limitation because then you have to rely on completely onboard sensors, or maybe you may have some stations for boosting your sensing, right? Or boosting your communications as well. So with all this, like it is very much dependent on the environment you are working on, your autonomous system is working on. So that's why it's a domain specific aspect. And it affects clearly the your perception about your environment, your localization yourself in the environment, then mapping of your environment, and recognition, like cognition of your environment, that how the environment is behaving to you, right? And then, of course, once you know all those things, when I'm saying behaving to you means I'm just talking about that how they are located, how they are heading, how they are maneuvering or accelerating, and all these things. And then, of course, it also affects as a result the strategy and policy sharing as well because of the communication linking problem or latency. There are like some, so of these things are very much domain specific or platform specific or problem specific. And there is something domain independent where we talk about different strategy planners, right? For the overall system, we may have some strategy plan. So, okay, these are the way we should plan our things, right? All, it's a very outer look thing. Then there is something called motion planners, right? You may have motion planners, and then you may be having motion planning algorithms, and then you may be having further implementation algorithms, decision making algorithms, right? In a comparatively lower loop, right? They are not they are not deciding the overall strategy, but at a lower level to make the decision, right? For example, like once you are on a corner of a road, you know that, okay, now I have to turn, right? Now, while turning, you should be knowing that, okay, you should not really go with the same high speed. You have to be careful. So all these decisions have to come. If you see something, if you feel that, if your system feels that there is something, some blockage is there, so gradually you should reduce your speed and try to understand whether it's a real blockage or it's just a virtual impression, which is not the real one. So all these things should be there, right? Accordingly, you need to have different kind of reactive control. Of course, you need to have a proactive control as well from the beginning. And then you need to have the behavioral coordination. So all these aspects are falling under the category of domain independent things, because uh, all these things, it has to be kind of somehow embedded into the system from a priori, right? You are setting up the things that, okay, these are the overall things. Now, if you see these, there maybe the lower level you can make some intelligent control algorithms or intelligent planning algorithms, which may make it more adaptable. But it is not dependent on purely on your dynamics, so to say, at the very basic level. You can have kinematics, just pure kinematics based equations. It's not associated with the vehicle dynamics even. Algorithms or planners, right? Pure kinematics based ones, and then you can just use it with the limitations of the domain specific aspect. Okay, next slide, please. Okay, so this is a schematic which is taken from a very celebrated book. I think many of you have already seen this book. And this is, of course, coming from a celebrated researcher in robotics, Segwart. So in this schematic, it's just like if you notice that there is a real world environment, of course, from which your system is sensing through, let's consider it's a fully autonomous in this particular operation. So it's sensing using its onboard sensors, right? And then it gets data, it extracts the required information, and it interprets. So there is a perception block. This whole together, this is the perception block. And then you know that, okay, this entire perception block then sending its understanding, right, which is coming in the form of its localization. It's it's a kind of map, and then which will be helping for the further localization. So then it goes to this localization map building, this portion, right? you have some understanding of the environment model surrounding you, their characteristics, motion characteristics, and everything. And then you also have a priori notion of a knowledge of database, particularly in kind of like military environment. When two combat vehicles are going to face off, then by seeing some signatures, they know, okay, this is the enemy fighter is like this. Okay, these have this kind of motion characteristics. So they know that, okay, how to react in those cases. So they're quite prepared from their knowledge of database. Now, this information are coming to the cognition path planning, right? Here, the mission is also setting some commands that separate more than whatever is happening here, whatever is, strategies and all that from the further outer loop is coming. This is coming as the mission commands to this cognition path planning, from which is finally generating the path. So you cognize the overall thing, and then you plan your path, and you send your path to the lower level controller, where the path execution, that is the low level control, is going to implement it. And then finally the actuators are like there is some actuator commands which is going to the actuators, and then actuators are working, so that overall system is then acting in some way. So this is the motion control part. Okay, so please next slide, please. Am I overshooting the time, or like can any of you please tell me that?
Yes, sir. Sir, the session was till 45. Maybe another 5 minutes we can extend.
That,
No
that
problem.
is there, right? Okay, then it's fine. Yeah. Okay. Now with all this understanding, now I'll try to give you some different research directions, which is of course a subset of the overall possible research directions. In field robotics, of course, you can look for like different aspects, and all these aspects, like it is research is going on continuously, and like lots of improvements are happening every other almost every other time. So you see that there is it's a nascent field, but again it's a much developed also in very rapidly. And people are coming up with algorithms, very efficient ones, and they are improving over the earlier ones, and in each and every aspect of it, right? So in field robotics, of course, like it looks for like, okay, to improve sensing capacities, to improve the overall perception block, and then of course like to improve the navigation capabilities. When you are improving the perception block, also parallelly, simultaneously, you should be able to improve the navigation block as well. Then you are having this motion or path planning, and then guidance and control, right? So you need to have efficient algorithms to use the data from the perception and navigation block more satisfactorily to achieve your purpose, right? To achieve your job. And then of course at the low level you need intelligent controls, which would taking care of different perturbations, different uncertainties, different variations in your vehicles or systems at low level. Right, and all these things may happen in unstructured environment or prior unknown environments. Right? And there is another aspect, that is human-centered robotics, where robots are basically used to support human beings. And again, like as I was telling that, okay, different kinds of teleoperations and all that. So in the potential application, we have already discussed this kind of. And in fundamental research, if you consider, then there are different things like this kind of SLAM and SLAP, that is simultaneous localization and mapping, and simultaneous localization and planning. So all these things are people are talking about. Then you have this, again, I'm getting some noise. I'm getting some noise. Can you please mute? Can you please mute? I don't know whose mic is on. Can you please mute yourself? Yeah. Okay. So we also have this human-robot interaction. So this is also a very specified field in some fundamental research. Lots of work is going on, because how robots can mimicry the human in the long run, and so that's the purpose of things. Then we are talking about swarms of systems, right? So we have robot teams in multi systems. So they are trying to do some work simultaneously. One kind of interesting problem that you may have already seen or known, that like autonomously having some autonomous football match of a swarm of robots, right, between two groups of robots. Okay, next slide, please. Okay, so this was the fundamental research, and then there is some applied research also. Like applied, when I'm saying about applied research means it's very specific to different kind of applications, so to say, where they're talking about this kind of infrastructure. To, as I gave you one example, that kind of monitoring or surveillance of the soil infrastructure, right? So you have the overall. It's not a very just a robot or in one single robot in that way. It's a complete system. So you can have infrastructure systems, monitoring systems, then as I told about different inspection operations there also. So these are very specific application specific design of your autonomous system. The earlier ones were like more like a kind of algorithm related. So earlier ones were more if, uh, like domain independent ones, fundamental researches. These things are more domain dependent ones because here the the vehicles or the agents or the system itself is very much involved. So right, so you it's not only that for any generic environment they can do in the same way. Yeah. So these are highlighted here. Please next slide. Okay, just a couple of slides. I will just take that one part of it is the very quintessential part. That's the motion planning, in which like here I have shown for one agent, but you would be basically having multiple agents, which will be having some initial locations and they would be having some goal locations. Now there may be some autonomy in the system to allocate these locations also, that going from where to where, and then the agents have to decide that how to plan their path, and then reactively once they face some another agent coming or some obstacle coming, they may be going on reactively modulating their path. So in this way they can look for this motion planning. So this overall field is called motion planning. This is fed from the navigation and perception block, right? Where you have from where you are getting where you, I mean you have a full cognitive model of the environment and yourself, your system also. Yeah. Next slide, please. Next slide, please. Uh, yeah. Okay, so broadly, there are 5 different kinds of things that I can talk about in this way. Like one is this offline motion planning, where you have prior knowledge of the environment. You can go for offline motion planning for different unmanned vehicles in the system, overall system. However, it should of course have some reactive mechanisms. That's why this online collision avoidance for such systems also comes into picture. There is completely devoid of all these things. You can have a completely guidance system which is always online. So you may be having a guidance system as well, where you're not talking about offline things, because online planning or replanning mechanisms must be there to avoid any kind of undesirable situation during the motion, right? So essentially, even if you may have something offline, which will be kind of open loop thing, you have to have some online mechanism embedded into it. And then that leads to a kind of application specific hybrid algorithms for this guidance and avoidance of different this unmanned systems. And then, of course, like you also can have a coordinated guidance. As I was telling that in multi-agent systems, you can have a coordinated task execution such that you are able to achieve some task more efficiently, more quickly. Yeah. So anyway, we don't have time to go to any detail of any of them. I hope that you will be having other discussions in which you will be getting more clear. Okay. So yeah, next slide, please. So to conclude, we have given a broad introduction of autonomous systems, and in which we have specifically talked about the different associated potentials and challenges and visions, and the potential applications also we have pointed out. Then different levels of autonomy we have defined and explained what we mean by autonomy, and when we say about autonomous system, what we should say actually, that a system is autonomous in a set of allocated works or tasks and our task profiles. I mean, then what are the different components? Broadly, we have just mentioned, and then what are the different research directions? A subset of it we have indicated. At the end, like we talked about the basic introduction classification of motion planning. Yeah. With this, thank you. Yeah, you can go to the next slide, which is just thank you slide. Yeah.
Participants, forum
Any
is open
question?
for questions. Yes. Sir. Any questions from participants are welcome.